Okay, so we've looked at indefinite integration, which is just finding an equation for some area somewhere. But now let's have a look at it when it's a bit more useful, when we actually have a graph with an actual area and an actual space to look for an area in. So here I've got the equation y equals minus x squared plus 2x plus 3. And with the help of Desmos, I sketched it on a little graph here. And what I've done is I've shaded in the area that we are going to want to try and find the area of. Now, if I gave you just this and this equation and I asked you to find the area of that, without integration, you're going to struggle. You might split it up into shapes, but no matter how many times you split it up, you're never going to get that perfect curve. It will be into little triangles, and at that point, you're just doing the trapezium rule. So what we're going to do is we're going to start off by integrating this. So I'm going to write it out properly. So it'll be the integral of minus x squared plus 2x plus 3 dx. And that is going to be equal to, well, let's use our power rules. First one, add 1 to the power. So I'll put my minus x, add 1 to the power, divide by the new power. Next one. 2x, add 1 to the power, so that becomes x squared, divide by the new power. And then, last one, 3x to the 0 basically becomes 3x to the 1, divide by the power is 1, and I just end up with, if I tidy this up, minus x cubed over 3 plus x squared, cancelling the 2's, plus 3x. If you want, differentiate that and make sure you get back to the start. Now, what I, of course, have forgotten here is my plus c. And despite this plus c being incredibly important, with definite integration, and only with definite integration, when there is a curve and an area, we can actually get rid of it. I'm not going to just do that, I'm going to show you why, but we can just ignore it. So, let's go from here. Now, I've got my general equation for the area, but how do I know that it's calculating this area here? Why wouldn't it be calculating, say, that area that I'm not covering up, or that area between my fingers? Well, the way that we do this is we give it bounds. We tell it between which x-coordinate and which x-coordinate. So if I want it to go between here and here, then I can almost draw a line on each, find my x-coordinates here, which by the way are minus 1 and 3, just solve the quadratic if you don't believe me, and I can say that those are my bounds. If I wanted to find this area in here, then, that'd be 1 and maybe 1.5, and they'd be my bounds. So it's important that we're always checking where exactly on the graph I would like my area to be. So what do I do with those bounds? Well, officially, what I should have done, and what I will be doing from now on, is you put them at the top and the bottom of your integral. So minus 1 at the bottom, 3 at the top. Smallest number at the bottom, largest at the top. Just notation so we know what we're doing. And now what I'm going to do is I've got my final answer and I'm going to stick it in some big old square brackets and I'm going to put my boundaries in there as well. This is just how we generally write these things. Now, what I'm going to do is I'm going to take my top number and I'm going to pop it into this equation instead of x. So let's do that now. So let's put my 3 in here. So I get minus 3 cubed, which is 27, divided by 3, which is 9. So I get minus 9. I'm going to keep this in brackets. Plus x squared, well, x is 3, so that's plus 9. Well, that's already looking pretty nice. Plus 3x, that's another 9. Plus c, which just gives us 9 plus c. Now what I'm going to do is I'm going to put my minus 1 into this equation. And I'm just going to put it over here. I'm going to leave a gap in the middle for now. I'm going to put a minus 1 in, and let's see what happens. So here we go. Let's see if I mess up a minus and have to re-edit. What are the odds? Minus 1 into the x. minus 1, 1, minus 1. That's minus 1 times minus 1 is 1 divided by 3 is 1 over 3. So far, so good. Plus minus 1 squared is 1. Plus 3 times minus 1 is minus 3 plus c. Let me simplify this. 1 minus 3 is minus 2. Minus 2 plus a third is minus 5 over 3. No cuts, no edits just yet. We'll see. So I've got 9 plus c and then minus 5 over 3. And I've already forgotten my c, plus c. And then simply, I'm going to subtract them from each other. Okay? The biggest one in first minus the smallest one. So I get 9 plus c minus 5 over 3 plus c. In just a space, I'm going to just pop this up here, in this little box. So I get 9 minus 5 over 3 is 9 plus 5 over 3. Yes, I can do that in my head. I just don't want to. And then c minus c. C minus c is 0, so I have no constant tagged on the end, which is why we could have ignored the c to begin with, because it just cancels out when we do this minusing. So my final answer for this area is 9 plus 5 root 3, which can't be simplified, units squared. It's an area, it'll be units squared, unless otherwise stated. So yeah, this is how you find the area under a graph. Now, I'm going to kind of skip to another portion here because I don't really think it needs its own video. These are more, lesson based. I will do more questions in other videos and the walkthroughs that I've started making. So I'd like to spend this time to discuss what happens in a situation like this. I've drawn a sine curve. Don't worry, we're not going to be integrating sine just yet. But I do want to get some ideas across, and then I'm going to use an example using some nice polynomials instead. If I wanted to find the area between here and here, well, that's no problem. Right, I just put in my bounds here and here, find that area, all good to go. But if I want to find my area between here and here, something weird happens. The graph goes negative, right? The x-coordinates are still positive, but my graph goes negative. And when my graph goes negative, weird stuff happens. And it's something that we need to keep on top of. So let me get rid of the sign, because that would be too scary too early. I'm going to replace it with something similar, and let's see what I mean. Okay, here's something a little bit more palatable, hopefully. Same idea, though. I've got an area underneath an x-axis. So what do I do? Well, you'd imagine just do the same thing. So let's do that. So the equation here is y equals x squared minus 5x. So hopefully just from looking at that equation, of course you can use a quadratic formula if you want, no shame in that. I get my boundary. My boundaries are 0 and 5. So I'm going to have an integral between 0 and 5 of x squared minus 5x dx. So let's integrate that. X squared, add 1 to the power 3, divide by that power. I get x cubed over 3. I'll use my nice square brackets. X squared over 3 minus, add 1 to the power, x squared minus 5x squared, divide by that power 2, minus 5x squared over 2. And that, again, is between 0 and 5. Now, am I going to be able to do this without rubbing anything out of the board? Let's find out. Let's move down here. Right, let's pop my 5 into the equation, same as we did earlier. I have left out the plus c because, as we've seen, if and only if it's a definite integral, the c does not matter. Only if it's not if it is a definite integral. If it's not a definite if it's not a definite integral, include the c. Plus c everywhere, but not here. Right, anyway, let's pop the 5 in. 5 cubed 125 over 3. I'm really going to stretch my mental maths here, aren't I? Just trying to get a double minus in there, don't need that. 5 squared is 25, times 5 is 125 divided by 2. So I get 125 over 3 minus 125 over 2. And then that whole thing is going to be minus, well, if I put 0 into this equation, 0 cubed is 0 minus 0 squared is 0. So I just get minus 0. Okay, good to go. So here's my area. 125 over 3 minus 125 over 2, which I can definitely do off the top of my head. Hey Siri, 125 over 3 minus 125 over 2 is about...
125 over 3 minus 125 over 2 is approximately negative 20.8333.
It's my brain. You heard. Minus 20.833. Now, here is my area. Personally, if I was sat in an exam without knowing about integration, and I saw a minus for my area, I'd probably assume I'd done something wrong. If I was adding up triangles or squares or just finding the area of a hexagon and I got negative 20, I would probably assume something's wrong. So I don't blame you if you look at this and you immediately go, something's afoot. That shouldn't be right. We can't have a negative area. How can something have a negative area? Well, the answer is it can, kind of. Anytime you do this calculation below a curve, or below the x-axis rather, with a curve, you will get a negative answer every time. No matter or where it is below the x-axis, no matter if it's a tiny part of the graph under the x-axis, you will always get a negative area. This is a problem. Luckily, it's got a very simple solution. Now, it's quite sophisticated, but essentially what I'm going to do, okay, pay attention. I'm going to take my minus 20.833 and I'm going to rub out the negative sign. Yeah, that'll do. What's that? My area is 20.833. Rub it out. Which is the correct mathematical thing to do. All those horrible minuses that you found in the past with time and distance, not displacement, and you wished you could just erase them, well, your day has arrived. You can just get rid of this one. It's almost a byproduct of integration itself that we expect the negative and we also know that it's false in our context. In our context of finding areas, it is going to be false. So we will just remove the minus and that is the area underneath this x-axis. Now, I think I will make another video discussing more complicated graphs rather than overloading this one. So in that video, I will show you what happens when we have a graph that has something that's both over the x-axis and under the x-axis, because it does require special treatment.